We present an interview study on how domain experts create conceptual diagrams and its implications for diagramming tool design. I'm Nemo from Carnegie Mellon University. Conceptual diagrams, also known as explanatory diagrams, concept visualization, describe a class of diagrams that provide a high-level graphical overview of a certain conceptual model, whether it be the structure of an LSTM network, how an encryption algorithm works, or how to order things at a local burger joint. People use them to explain and communicate concepts efficiently in all kinds of media, on web pages, in academic papers, in books, and on YouTube channels. Conceptual diagrams tend to be abstract and topological, in that the physical placement of shapes and labels don't matter as much, as long as it illustrates the same concept. Consider a graph showing how some nodes connect. The change of the node positions doesn't really change the meaning of the diagram. The relationships are topological. In addition to these nice properties, people also found that diagrams improve students' learning and make teaching easier. They're positively correlated with the impact of scientific publications, and let's be honest, nice diagrams are a pleasure to look at. However, much is unknown about how people create these pretty diagrams. One reasonable guess is that people start with some informal sketches and later translate them into better-looking final diagrams. But how do diagrams evolve from sketches to their digital forms? At what point does the diagrammer decide to switch tools? How do diagrammers manage their evolution of diagrams in general? What tool, if not multiple tools, are chosen? For what purposes? Are there any barriers when using them? What kinds of affordances do they provide? We had a lot of questions. So we decided to conduct semi-structured interviews with 18 diagrammers from 12 different domains, ranging from architects to K-12 educators to mathematicians. Following the interviews, we performed thematic analysis on the verbal data to extract high-level themes as well as insights to designing the next generation of diagramming tools. We grouped the codes from our thematic analysis into 3 high-level themes. The first one I'll introduce is representation finding. By representation, we're referring to visual representation, how abstract information is represented pictorially. To illustrate this concept, let me show you an example from a seminal paper on diagramming by Joe Larkin and Herb Simon. Consider a truck moving rightward on the screen, and think about what forces are exerted onto car B, and how you will visualize it. A standard representation is free body diagrams, where the truck becomes a mass point and the forces are arrows with magnitudes. You can also represent them as circles, or if you're hungry, chocolate bars. But there are problems with the last two. The circle diagram loses the directionality of the forces, and the chocolate bars might be too weird for everyone to understand. The main message is, appropriate representations distill complex information by boiling them down to the essence, and not all are equally effective in different contexts. Since representations are so important, our participants reported the process of representation finding by seeking existing standards in their domains. For instance, in computer graphics, the view angle or the camera in rendering diagrams tend to be represented as an eye icon and the light source as a little sun. In the absence of existing standards, some diagrammers create their own ones, like these diagrams showing the structure of certain mathematical groups created by one of our participants. In this process of finding visual representations, sketching using pen and paper becomes an important tool for exploring design alternatives and evolving their visual representations, like how one participant evolved the design of a projector calibration system by inventing different kinds of arrows to denote more complex configurations. The representation finding process is creative and rewarding. Like P1 stated, "Why didn't anybody draw that picture before? I've been taking something that almost seemed to be completely confusing or unimportant, and having a picture that makes you know what's going on is truly satisfying." Next, we'll talk about the tools that our participants use and why they make their choices. In general, the diagramming tools that they use fall into one of two categories, differentiated by their dominant mode of interaction. Direct manipulation or WYSIWYG tools have graphical interfaces and allow you to directly create and manipulate shapes. The programming language-based tools have textual interfaces and often involve typing snippets of code into an editor and compiling the program to view the diagram. Examples of language-based tools include D3, TXE in Tech, and Matplotlib in Python. For direct manipulation tools, our participants mentioned tools like Adobe Illustrator and Figma. For programming languages, most of their users reported better support for abstraction and automation of workflow. They also suggested that textual inputs give them better control locally, like how to precisely place a shape. Common drawbacks of PL tools include a steeper learning curve and the higher upfront costs for constructing diagrams due to the compile and run cycles required, and the complexity of the languages. For direct manipulation tools, our participants like their faster feedback cycles and the ability to see and control how shapes relate to each other globally. The cost of this is that the drawing process tends to be highly manual, and the diagram interface can be very viscous. In other words, once drawn, it's tedious to make a change because many of their shapes need to be manipulated manually to accommodate the new change. The pros and cons of these two kinds of diagramming tools lead to interesting patterns for automation and reuse. We saw from some participants an interesting pattern of backtracking. One example is by literally keeping the whole history of the diagram as separate artboards in Illustrator, not just linearly, but also with branches. Other diagrammers maintain the consistency across their work by keeping a text file with low-level parameters like color codes and line widths because the tools don't always remember them. To keep track of their visual representations, some participants also curate a library of mini diagrams such that they can build on top of those examples when they create similar diagrams. In addition to learning a great deal about how people diagram and appreciating their beautiful work, we also saw some gaps in their diagramming workflows. Our participants search, adopt, create, and iterate on their representations outside of their digital diagramming tools, but prefer lower-stake medium such as pen and paper. This is in part due to the limitations of both direct manipulation and language-based tools. For instance, languages are reusable and powerful, but require more time and effort. On the other hand, GUI tools are flexible, but require you to commit to a representation up front without the ability to change them easily. All of the above lead to various ad hoc workarounds to maintain and reuse diagram elements without strong support from the tools themselves. The net result is that diagrammers are often sadly deviated from the creative core of diagramming because their tools are limited. Can we fix this? How can we design a tool that provides a more natural experience just like pen and paper, but with the additional benefits of the power of computing? Inspired by these observations and an extensive review of related literatures both in and outside of HCI, we present some opportunities to guide future designs of diagramming tools. We collectively call them a natural diagramming experience. We adopt the term natural from natural programming, meaning that the diagrammer can express their ideas in the same way they think about it. We describe natural diagramming in 4 dimensions in our paper. In this video, we'll only go into 2 of them here, but I invite you to read our paper for more content. Given the importance of representation finding and reuse in our results, we argue that a natural diagramming tool should treat representations as first-class entities, potentially by explicitly encoding the concept being drawn, and the mappings from the concept to concrete geometries, just like how cameras are represented as eyes or function as curves or flows between axes. Visual grammars have been very successful in the domain of data visualization. Many popular data viz tools like D3 and VegaLite built on a visual grammar called the grammar of graphics, which let people encode, transform, and map data attributes to visual properties. Other systems like Penrose propose grammars for domain outside of data viz. For math diagramming, Penrose let users directly write down abstract concepts as a declarative program, and the visual mappings as another. Different from VegaLite, Penrose maps math notations to constraints instead of data. This allows the system to generate a whole space of possible diagrams with the same meaning or semantics. The power of these systems comes from a salient encoding of visual representations, which opens the possibility for reusable representations for different contents, and therefore faster or even automated exploration of design alternatives. Penrose and Vega Light encode representations by introducing a higher level of abstractions, but it comes with a cost. As suggested by our participants, the sense of agency or engagement is deeply valued for diagramming, as well as the ability to have immediate visual feedback. The extra layer of indirection introduced in Penrose and Vega Light prevents users from freely editing the diagrams, and in part take away the sense of engagement in the diagramming process. Efforts to bring programmability to direct manipulation and liveness and engagement to programming, like ProDirect manipulation, attempt to bridge this gap. ProDirect systems attempt to propagate changes between textual and graphical views bidirectionally. Closely related, live programming is a new programming paradigm, where the output updates in real time as the programmer interacts with the program itself, often in novel ways that go beyond traditional GUI or textual interactions. Similarly, programmable brushes, such as dynamic brushes, allow users to program the behavior of brush strokes for procedural and generative arts. These techniques, although currently limited to their domains, provide promising directions towards bridging the gap between programming and direct manipulation for conceptual diagramming tools. For more discussions on related work and other natural diagramming opportunities, please refer to our paper by following the link. Thank you for your attention.